Hello students, this is Mr. Allen here, and today we are going to look at section 4.1, which will begin our journey on integration. So section 4.1 refers to something called an antiderivative and indefinite integration. Our objectives here are to write the general solution of a differential equation and use indefinite integration notation for antiderivatives. We want to use some basic integration rules to find antiderivatives and find the particular solution of a differential equation. So we already know what a derivative is. So for example, if we know the function, well, let's turn it around. What if I know that there's some function f that is 3x squared and you want to use your knowledge of derivatives to figure out what the function was that gave you that derivative? Well, most of you would probably already figure out that that would be the function x cubed, because the derivative of x cubed is 3x squared. So we would say that this capital F function is the antiderivative of the little f function. And that is our definition for an antiderivative, which can be seen at the bottom. A function f is an antiderivative of f. Notice it's capital F and then lowercase f, if the derivative of capital F is equal to little f for all x in that interval. Just note that capital F is called an antiderivative of f rather than the antiderivative of f. Consider the following. What if capital F was x cubed? Or what if capital F was x cubed minus 5? Or what if capital F was x cubed plus 97? It turns out that all of those functions have antiderivatives that are equal to 3x squared. In fact, for any constant c, the function capital F of x equals x cubed plus c is an antiderivative of f. So theorem 4.1, this is important, so I would put a star on this slide. Representation of antiderivatives. If capital F is an antiderivative of f on the interval I, then g is an antiderivative of little f on the interval I, if and only if g is of the form g of x equals f of x plus c for all x in the interval where c is a constant. Using this theorem, you can represent the entire family of antiderivatives of a function. So for example, x squared, the derivative is 2x. So you can represent the family of all of the antiderivatives for the function 2x by g of x equals x squared plus c. This is called the family of antiderivatives, where c is constant. This c is called the constant of integration. The family of functions represented by g is the general antiderivative of f, and the general solution is given for the differential equation is g prime of x equals 2x. That's a differential equation. It's a derivative. That's why we call it a differential, and it has an equal sign. That's why it's an equation. And there's the definition right below. So it turns out that y prime equals 3x is a differential equation, as y prime equals x squared plus 1 is also a differential equation. So let's look at a very simple solution for a differential equation. Y prime equals 2. So what would be the antiderivative of 2? Well, hopefully you would realize that the antiderivative of 2 is 2x. Therefore, the general solution would be y equals 2x plus c. So the antiderivative of y prime equals 2x. In fact, let me go ahead and write this down. So the question is, the derivative of what is equal to 2? Well, hopefully you realize that that is x, 2x. So then we just need to add that constant of integration. And basically what we're saying then is any equation of this form, which by the way, those are all linear, when you do the derivative of them, they will give you 2, because the slopes of the tangent, or the slope of the line, any of those lines is 2. When solving a differential equation of this form, dy dx equals f of x, it is convenient to write the equivalent differential form. So in other words, we could multiply this dx over here to the other side. The operation of finding all solutions of an equation is called anti-differentiation or indefinite integration, which, by the way, this is the title of this section that we're looking at today, and is denoted with this sign right here. This is actually a sigma sign, but it's kind of like a fancy S. So here's the formal notation that we use. We would say that y equals, and now we've got this integral symbol, f of x dx. So the dx tells us the variable that we're integrating with respect to, and then the integrand is simply the function that we're integrating. Capital F of x is what we call the antiderivative of f, and c is the constant of integration. This is called an indefinite integral and is synonymous with the antiderivative. The inverse nature of integration and differentiation can be verified by substituting capital F prime for f of x for the indefinite integration definition we obtained below. So if we integrate this, we can just go ahead and do the derivative on both sides and we will get this. So now here's the bad news, folks. You guys should know your differentiation rules. Now you're going to have to know how to use those in the other direction. So these are all of our integration formulas. So for example, if I said, what is the integral of 2 dx? Well, we've already seen that. That'd be 2x plus c. That'd be that answer. You need to know your power rule. This one right here is probably the most important one, the power rule. You need to know, for example, that the antiderivative of cosine is sine because the derivative of sine is cosine. And then here's some more. For example, you guys learned that the derivative of tangent x was secant squared x. So now you need to know that the antiderivative of secant x squared is tangent x plus c. Another one, these here are really important. The integral, these here. These guys right here, these are really important ones to make sure that you're aware of, okay? So for example, if we want to integrate this, what we're going to do is we've got to simply think of this as like our power rule. And so we're gonna, we could just cheat here if you wanted to. We could simply just say, we could just simply say that, well, it's got to be x. Oh, I'm still on the eraser. Let's go ahead and do this a little bit more formally. So you got to ask yourself, what is going to be the antiderivative of that? Well, one of the things we can do is we can rewrite this as the integral of 3x to the first dx. That's the same thing. So now what we're going to do is we're going to use our power rule in reverse. So I'm not going to go back to the previous slides, but the power rule says what we need to do here is we need to add 1 to this exponent, which is the opposite of subtracting, and then we have to divide that amount down here, this 1 plus 1. In other words, this antiderivative, and I'm going to go ahead and keep it in red, is going to be 3/2 x squared plus c. That's the antiderivative. Okay. This is the integral, if you will. Now we can check that. The way we check that, I'll do that in green, is just do the derivative. So what is the derivative of what we just did, which was 3/2 x squared plus c? Now keep in mind that c is a number. It's a constant. So the derivative of that will be 0. So this part here is going to go to 0. But now I've got to deal with this part here. So now I'm going to use my power rule. So that's going to be 3/2 times 2 times x to the 2 minus 1, which is 1. The 2's are going to cancel, and you're left with 3x, which is exactly where we started. So that is the correct answer. So 3/2 x squared plus 3c is can be rewritten in a simpler form as what I have here. Actually, I guess I should maybe make this note here. And I apologize for not doing. Remember, c is just a constant. It turns out that C times 2 is the same thing as C. 1/2 of C is the same thing as C. In fact, C plus C is C. Okay, so a couple of notes here. A lot of times what we'll do when we're doing integrals is we will use we have the original integral, we will rewrite that integral, we will then integrate, and then we will simplify. So here's an example to look at this particular equation. So to solve this, we need to find the antiderivative of this, which is x squared minus x plus c. Okay, so that's going to be y. And hopefully you can see that, oops, this is cubed. X cubed minus x plus c. And for any c, as we can see here, that these are all cubic curves. These are all cubic curves. And in this case right here, I'll try to draw this one right here, which I kind of hit. That is the case when c is equal to 0. If c is equal to 1, then it's the one right above that. Each of these antiderivatives is a solution for the differential equation. dy dx equals 3x squared minus 1. So this should look kind of familiar because that's what we had in here. Many applications of integration. You're given enough information to determine the particular solution. So this was what we call the general solution. This right here, this was the general solution. The particular solution would be when we just plug one of these in. So in this case, when I said C is equal to this bold one there, that's the particular solution. Typically, in order to find the particular solution, you need to use an initial, you need to have an initial condition. For example, passing through the point 24. So let's go ahead and do one more example here. So here is my differential equation. This could have also be rewritten as dy dx equals e to the x. We are given the initial condition of f of 0 is equal to 3. So here's what we need to do. We need to say that f is going to be equal to the integral of e to the x dx, because that's the variable that we're integrating with respect to. So when we integrate that, we use our antiderivative for e to the x, which is e to the x. So we could say that f equals e to the x plus c. That is our general solution. Now, to find the particular solution, we're going to need to use this information right here. And that's telling us that when x is equal to 0, y is equal to 3, or f of 0 is 3. So what we're going to have to do is we're going to substitute 3 in for f and 0 in for x. And we will see that, no pun intended, c in this case is going to be equal to 2. Because e to the 0 is 1, 3 minus 1 is 2. So the particular solution here is f of x equals e to the x plus 2. That's our answer. So here's our particular solution again. It is this curve right here. All the other curves, not all of the other curves, but several of the other curves have been drawn on here. So for example, when c is equal to 3, that'd be this top curve. When c is equal to -3, that'd be this bottom curve. The particular solution that we were interested in was this one right here when it goes through 0, 3. When it went through 0, 3. That's it.